So section 8.4, the examples that go with this, if I'm finding the area between curves, instead of finding the area, again, I keep saying with respect to the x-axis, now we're finding in between. We have two options. We could think of it one way, find the area under the upper curve minus the area under the lower curve. The upper curve in this case happens to be g of x. That's that one there. And the linear function is f of x. So that means that find the integral of from, I guess we're going from -1 to 3 of g is the upper curve. Whoops. G of x dx minus the from -1 to 3 of f of x dx, like that. That's one option. The other option is to think, I tend to think this way, but you know, whatever works for you. I tend to think, oh, we have our rectangles here, and I used left here, not that it matters, but this maybe I'll do right. That makes more sense. Here, the right side, here, my dx, and then my upper function was g of x minus f of x is going to give me the length of each of those rectangles. And the way we sum up the areas of those rectangles is use an integral. So here, length of each rectangle and width of each rectangle. Again, it's a stylistic thing, right? And then just solve for it. Bounded. And these are just the integration rules. Hopefully you know those by now. So then I would take g of x and subtract f of x. Don't forget to change the signs, of f of x here. So when I distribute the negative, you can combine like terms or whichever way you do it, right? Now for this one, and again, for some people, it's a struggle to kind of figure out which is the upper and which is the lower. In this case, our upper is f of x and my lower is g of x. So if you want to find the area of under the curve for f of x and then subtract the area under the curve for g of x, whichever works best for you. But same idea, you're told the boundaries. Again, minus a -2 sign of x over 2, a negative minus a negative becomes a plus. That's why it's a plus there. Now, the only way I could make it a little more interesting, I feel like, is if we have something like this. So now it's saying find the area between the two curves given. So now if I'm saying it's bounded by the curves, now I could change things around, and I'll do that on the side in a second. But our first job is then to figure out what the boundaries are. So essentially, it's asking you to find this area in here. So now you have to figure out which is going to be the upper, but you also need to figure out the boundaries in this case. It turns out to be nice values, but let's say they weren't so nice. Your first job is then to figure that out. So step number 1 is to find the points of intersection of f of g at f of x and g of x. So set the two equal to each other and then solve. In this case, they happen to factor nicely, and we end up at -1 down here. So -1 is one and 3 is the other. That's my job number 1, is to find the boundaries. Then we're going to move on and integrate. The upper function in our case is f of x. That's the parabola that's facing down. And the lower function is g of x in this case, because here is my f of x and here is my g of x. And then you just proceed as normal. You just go forward, substitute in for the functions like that, simplify a little bit, integrate, and then put in the boundaries and find the value. Now try B. Pause the video and try B on your own. I'll show you the answer in a second. So first, find the intersections, positive, -2. If you notice that this happens to be symmetrical, it's a little hard. How sweet. It's symmetrical. then you could just go from 0 to 2 and double that. That would also work. Any of those things would work. But I just want to add like a little interesting, if I had something like this, and we have an upper function is f of x, looks like this, and then a lower function, let's call that g of x. And I told you all to find the boundary or the area between the two curves from A to B. That means the relationship between f of x and g of x changes. So you would have to find that point of intersection right here. Whoops, why did that make a little line there? You would have to find a point of intersection right there. Let's call it, undo. I don't know why I'm doing it. Let's call this order pair CD. That means then my integral would go from A to C, the point of intersection, and then at first I have the f function is the upper function minus the g function, dx. And then I would have to then add the area from C to B, and then now the relationship changes because the g function, g of x, the orange one is on top, minus f of x is on the bottom, is the lower function dx. So if the relationship between f and g changes, I have to find where the relationship changes and split the function in, or split the integral in two. You can't, so it would be essentially from A to B, the absolute value of f of x minus g of x, like that, dx. But anytime you do an integral of an absolute value, you have to see it where it changes from positive to negative there. If it changes to negative, you have to flip-flop the relationship. So that's basically what we're doing here up at the top. So these two things are the same thing. So anytime you have an absolute value in there, you would have to be careful that the where the relationship changes. So you would still have to figure out where f of x and g of x are equal to each other, or f of x minus g of x is equal to 0, and then check if the relationship changes at that point. And then I would have to split it into two. So that's how I could make that part interesting. So first you're finding this area here where f of x is on top. That's the blue one. And then the yellow one that's in here up to B, that would be this one here. So that's how to handle if it happens to switch positions.